A tank circuit, also known as a resonant circuit, is a type of electronic circuit that uses a combination of inductors and capacitors to create a resonant frequency. It is a common building block in many types of electronic circuits, including radio receivers, transmitters, filters, and oscillators. The tank circuit operates on the principle of resonance, which is a phenomenon that occurs when a system is driven at its natural frequency. In the case of a tank circuit, the combination of the inductor and capacitor produces a natural resonant frequency, which can be used to filter or amplify specific frequencies in an electronic signal. The tank circuit consists of a series or parallel arrangement of an inductor and a capacitor. The inductor, which is typically a coil of wire, stores energy in a magnetic field when a current passes through it. The capacitor, on the other hand, stores energy in an electric field between its two plates when a voltage is applied across it. When the tank circuit is excited by a signal at its resonant frequency, the energy stored in the inductor and capacitor is exchanged back and forth between them, resulting in a sustained oscillation. This oscillation can be used to filter out unwanted frequencies or amplify specific frequencies, depending on how the tank circuit is configured. In addition to its use in electronic circuits, the tank circuit has applications in other fields as well, such as in the design of musical instruments and acoustics. The resonant frequency of a tank circuit can also be affected by external factors such as temperature and humidity, which must be taken into account when designing and using these circuits. Overall, the tank circuit is a versatile and important component in the world of electronics, with a wide range of applications across various fields. The design and characteristics of a tank circuit depend on the specific application and desired resonant frequency. However, there are some general principles and parameters that are commonly used in tank circuit design. The resonant frequency of a tank circuit is determined by the values of the inductor and capacitor. The resonant frequency can be calculated using the following equation. F equals 1, 2I diaresis as LC, where F is the resonant frequency in Hertz, L is the inductance in henries, and C is the capacitance in farads. To achieve a specific resonant frequency, the values of the inductor and capacitor must be carefully chosen. In general, the inductor should have a high Q factor, which is a measure of its efficiency and energy loss. The capacitor should have a low ESR, equivalent series resistance, and a high dielectric strength. The quality factor, Q, of a tank circuit is a measure of its selectivity and bandwidth. A higher Q value indicates a narrower bandwidth and higher selectivity, while a lower Q value indicates a wider bandwidth and lower selectivity. The Q value can be calculated using the following equation. Q equals 2I diaresis FL, R, where R is the total resistance in the circuit. Another important characteristic of a tank circuit is its impedance. At the resonant frequency, the impedance of the tank circuit is purely resistive, with no reactive components. This means that the circuit is highly efficient at transferring energy at the resonant frequency. However, at frequencies above or below the resonant frequency, the impedance becomes reactive, which can lead to energy loss and reduced efficiency. This is why tank circuits are often used in combination with other components, such as filters, to achieve the desired frequency response. Overall, the design and characteristics of a tank circuit depend on the specific application and desired resonant frequency. However, by carefully choosing the values of the inductor and capacitor, and paying attention to the Q factor and impedance, a highly efficient and selective circuit can be created for a wide range of electronic applications. Tank circuits have several advantages and disadvantages that should be considered when designing and using them. Advantages: selectivity. Tank circuits are highly selective, which means they can be used to filter out unwanted frequencies and amplify specific frequencies. This makes them useful in a wide range of electronic applications, such as in radio receivers and transmitters. Efficiency. At the resonant frequency, the impedance of the tank circuit is purely resistive, which means that it is highly efficient at transferring energy. This can lead to higher overall efficiency and reduced energy loss. Simple design. Tank circuits have a relatively simple design and are easy to construct, which makes them a popular choice for hobbyists and DIY projects. Versatility. Tank circuits can be used in a wide range of electronic applications, including filters, oscillators, and amplifiers. Disadvantages. Narrow bandwidth. The selectivity of tank circuits comes at the expense of a narrow bandwidth. This means that they are only effective at a specific resonant frequency and may not be suitable for applications that require a wide frequency range. Sensitivity to external factors. The resonant frequency of a tank circuit can be affected by external factors such as temperature and humidity, which may require additional measures to ensure stability and reliability. Limited power handling. Tank circuits may have limited power handling capabilities, which may make them unsuitable for high-power applications. Component tolerances. The resonant frequency of a tank circuit is highly dependent on the values of the inductor and capacitor, which may require careful component selection and calibration to ensure accurate performance. Overall, tank circuits are a useful and versatile component in electronic circuits, with advantages such as selectivity, efficiency, and simplicity. However, their narrow bandwidth, sensitivity to external factors, and limited power handling capabilities may make them unsuitable for certain applications. Tank circuits have a wide range of applications and uses in various fields of electronics. Here are some examples. Radio receivers and transmitters. Tank circuits are commonly used in radio receivers and transmitters to select specific frequencies and filter out unwanted frequencies. They are an essential component in the tuning circuits of AM, FM, and shortwave radios. Oscillators. Tank circuits can be used as the frequency-determining element in oscillators, such as crystal oscillators and LC oscillators. They are used to generate a stable and precise frequency signal for a variety of applications, including clocks, timing circuits, and radio frequency (RF) applications. Filters. Tank circuits are used in various types of filters, including low-pass, high-pass, and band-pass filters. They are effective at filtering out specific frequencies and can be used in audio, video, and RF applications. Amplifiers. Tank circuits can be used as part of amplifiers to selectively amplify certain frequencies. For example, in a tuned amplifier, the tank circuit is used to amplify a specific frequency and attenuate other frequencies. Musical instruments. Tank circuits are used in some musical instruments, such as electric guitars and synthesizers. They can be used to create resonant frequencies that produce unique and interesting sounds. Acoustics. Tank circuits can be used in acoustics to study the resonant frequencies of objects and materials. This information can be used to design better acoustical spaces, improve musical instruments, and enhance sound systems. Overall, tank circuits are a versatile and important component in electronics, with a wide range of applications in various fields. Their ability to selectively filter or amplify specific frequencies makes them an essential component in many types of electronic circuits, including radios, oscillators, filters, and amplifiers.